Alright, so today we're continuing our little mini topic on numerical integration and Riemann sums. Using Riemann sums to estimate integrals. So last time we just practiced calculating Riemann sums. So this gives us an estimate, and then of course the immediate question is how good is the estimate? Last time we did an estimate that was pretty bad, right? We had about 2.4 as an estimate for 8/9. So it would be good to have some sense of how good these estimates are. So error analysis is kind of different than most of our calculations. So I'm going to say a little bit about why this is hard or different from what we're used to. One is we're trying to measure the difference of something that we know minus something that we don't. Right? So we know, say, a Riemann sum, and we don't know the integral. And how do you tell how far apart two things are if you don't know what one of them is? That's kind of what makes this tricky. And it turns out that what we end up having to do is a lot of algebra with inequalities. So the calculations involve inequalities, which are less familiar than equations. Most of the time when we're doing algebra, we're solving equations, rearranging equations, dealing with equations. Inequalities are less familiar, and the set of moves that you have available is not quite the same. So it's a much less familiar territory, but this is one case where it's necessary to deal with the algebra of inequalities, not just equations. Precisely because equations deal with exact amounts, and we don't know what this is. Okay, so the starting point for our error analysis is an inequality that shows up in the book without any particular fanfare. And I call it the basic integral bounds theorem. The book does not give it a name, but I find that it's nice to have some kind of name for things, or I'll just call it the BIB theorem. At least have something to call it. And it goes like this. Suppose lowercase m and capital M are two numbers such that a function f of x is between them, between lowercase m and capital M, on some interval, a, b, meaning for all x in that interval. Then the theorem says the integral from a to b is between m times b minus a and m times b minus a. All right. So this is what I'm going to call the basic integral bounds theorem, just so I have something to call it. In the book, I said this no particular fanfare. This is equation 8. Although it's really more of an inequality. It's in a little box on page 277. That's in chapter 5.2, which is where the definite integral is introduced for the first time. So big chapter, 5.2, and trying to get at the concept of a definite integral. Lots of different facts flying around. This is one of them, which is one of the least emphasized because there's 100 things to say about the definite integral. Okay, but we're going to kind of focus on this for today and its implications. So let's think about why this is. proof slash explanation. And I'll give you two explanations. One of them is visual and one of them is algebraic. So the algebraic explanation is that you can integrate both sides of an inequality. This isn't something that we've done that much, but there's like this comparison theorem. If this function is bigger than this one, then it has a bigger integral. So this constant function, right, this is a constant function. For all x in the interval a, b, the constant function m is less than or equal to the function f of x, so we can integrate both sides. So the integral from a to b of the constant function m dx is less than or equal to the integral of this other function f. That itself is using a previous fact about integrals, this kind of comparison theorem. Bigger functions have bigger integrals. Well, the integral of a constant is just a constant times x, m times x evaluated from a to b. That's less than or equal to this integral. And so that's just m times quantity b minus a is less than or equal to the integral. And that's half of the claim, right? We sort of proved this. The other half proceeds in exactly the same way. Right? F of x is less than or equal to the constant function, capital M. Integrate both sides. And so we'll say the other half of the claim similarly. Okay, so that's how you can calculate your way to this theorem, this result. It's also quite clear from a picture. Can anybody describe what visual or fact about areas this corresponds to? What's that saying? Function. So capital M is some value that's bigger than this function all across the interval. Let's say maybe here. Okay. Bigger than all the values of the function on that interval. And lowercase m is smaller than all the values of the function on that interval. Let's say that's like down here maybe. Well, m times b minus a is the area of this rectangle. Capital M times b minus a is the area of this rectangle. And the integral that we're after is this region here under the curve. Well, this area comparison is just amounts to the fact that the area of a subset is less than or equal to the area of the total set. The green rectangle is contained within the yellow region, which is contained within the red region, so the areas have to go in that order. That's all there is to it. Okay, so using the basic integral balance theorem, if we have an integral that we may not know exactly, we can at least find upper and lower bounds for it. We can find numbers where we can sort of guarantee it's bigger than this and less than that. Use the basic integral balance theorem to find upper and lower bounds for the integral from, let's say, 0 to pi halves of cosine to the fourth of x dx. All right, so cosine to the fourth is an integral that, in theory, we know how to do exactly. How do you do cosine to the fourth? broad outline.
Split it into cosine squared, cosine squared.
Yep.
Replace one in so replace one of the cosine squareds with 1 minus sine squared. So you have cosine squared x minus cosine squared x sine squared x.
That would be great for cosine cubed, or cosine to the fifth. For cosine to the fourth, I want to call that cosine squared squared. And Elizabeth, what do I do after that?
You're going to want to use the double angle theorem.
Yeah, so 1 plus cosine 2x over 2, the whole thing squared. Expand that out, one of the terms involves cosine squared of 2x, which is 1 plus cosine of 4x over 2. Rearrange, eventually you can do the end. All right, so we could do this, but let's just try to find some bounds, bigger than blah, less than blah. So in order to do that, we need to find upper and lower bounds for this function. How big and how small can cosine to the fourth be? Well, for all x, actually for all x anywhere, not just on this interval. One thing I know about cosine to the fourth is it's always positive, or at least non-negative. It's an even power, right? So which means it's the square of something. Cosine squared actually is what we're just talking about. So if you square a real number, there's no way that's negative. So 0 is a lower bound for the function on this interval. How big could it be? How big do cosines get? 1. So I didn't say they had to be very sharp bounds, but at least this is at least true. Cosine to the fourth is always between 0 and 1. Thus, 0 times pi halves minus 0 is less than or equal to this integral. Which is less than or equal to 1 times pi halves minus 0. So, well, okay, those are pretty easy to simple. But the integral is between 0 and pi halves. That would be my answer to this between 0 and pi halves. Okay, pi halves is about 1.57. So the integral falls somewhere between 0 and about 1.57. That doesn't tell us the integral very precisely, but it tells us something. Suppose you were trying to do it the other way and you were using all your double angle lisses and cosines to the fourth, the others, dot, 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 and after 20 minutes of work, your answer was like 6. Okay. With a few seconds, you can determine that that answer is off. Right? This is a pretty quick error check that tells you if you're at least in the right range. Okay. So, as a sub-question, a side question, the basic integral balance theorem. How do you find M and N? Well, there's a few different tricks out there, a few different options. There isn't a single recipe. For sines and cosines, sines and cosines take values between plus and minus 1. Are between plus or minus 1. And that's often the beginning of an analysis that will tell you some upper and lower bounds. In this case, cosine to the fourth is true that it's between plus and minus 1, but we were able to do better because we also knew it was positive. Squares are positive, that's another one. So if your function is something squared, you can use 0 for your lower bound. could we use to find upper and lower bounds for a function? Yeah.
Look at derivatives.
Yep, and then what would that tell you?
You can find like maximums, and then you can also find where the graph's increasing.
Yeah, yeah. So there's two ideas in there, both of which we'll say something about, and I'll come back to that increasing idea because there's a lot there. But in principle, you could find the max and min. Now, we're not going to actually follow this very often, but this is a standard Calc 1 problem. Find the max and min of this function on this interval. You find the critical points, you evaluate f at the critical points and the endpoints, you compare the results, you find where it's largest and smallest. So m could be the min of f on the interval, and capital M could be the max, and away you go. So if you want to run that whole routine of solving for the critical points, dot, 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 you can use that to find upper and lower bounds. Come back to the increasing idea in a moment, because that's going to be an important set of tools that comes out of that. But first I want to talk about how to make this a little bit less crude. We saw for cosine to the fourth that our upper and lower bounds for the integral were pretty far apart, 1.57. So if I'm trying to approximately determine the value of the integral, I know an interval of width 1.57 that it falls somewhere in. I'd like to narrow that, right? I'd like to find a smaller interval that contains it. And you can do that by sort of pushing to a Riemann sum. You can think of the basic integral bounds theorem as telling you something about a Riemann sum with n equals 1. Right? The basic integral bounds theorem corresponds to, I'm going to draw one rectangle and compare its area to the area of my graph. And it's either too big or too small. Okay? But what if I draw several rectangles? Maybe I can get tighter bounds. So let's use the basic integral bounds with Riemann sums. There's an idea that I'm going to follow here for a few minutes. It's going to turn out to run into some snags in general, but then there are going to be special cases where it works. So let's suppose that I have my Riemann sum picture. So A, B, I have my function, and I'm going to chop it up with some partition points. And so I have all these subintervals, x2, x3, and so on. The idea here is I can do this lowercase m, uppercase m analysis on this interval, and on this interval, and on this interval, and on this interval separately. So on this interval, maybe I have a rectangle that I know is too small, and a rectangle that I know is too big. And on this interval, I have a rectangle that I know is too small, and one that I know is too big, and so on. I can use the total of all the yellow rectangles as an underestimate for my function, and the total of all the red areas as an overestimate. So the way that I'm going to do this with all the subscripts flying around and everything is to suppose that lowercase m sub k is a lower bound for my function, and uppercase m sub k is an upper bound on the kth subinterval, on the interval from, say, x k minus 1 to x k. Okay, so k equals 1 is this first subinterval, k equals 2 is the second subinterval, and so on. Applying basic integral bounds on each subinterval is going to tell me that the sum of all of the mk's times delta x is too small because using the sum of all of the capital MK's is too big. Essentially, I'm breaking up my integral into the integral over this interval, plus this integral, plus this integral, plus this integral, plus this integral. And each of those sub-integrals on all the sub-intervals, I can find these upper and lower bounds for. Okay. This can be considerably more informative than just using the basic integral bounds for a wide interval. Now, we're not going to try to follow this very far in this abstract way. You can maybe see an obstacle already. What might make this fact, it's a useful fact, but what might make it difficult to apply? In order to get anywhere with this, I have to find a whole bunch of little MK's and a whole bunch of capital MK's. Let's suppose I'm chopping my interval up to 100 different subintervals. I've got 200 bounds to go find before I can even do this. I need to find for each of 100 subintervals an upper bound on that region and a lower bound on that region. And then I can dump those results into this statement. If I'm doing that by, say, solving optimization problems, Calc 1 style, setting the derivatives to 0, I've got 100 optimization problems to solve. Then I'm going to take the results and add them up and get some information. Not really saving ourselves a lot of work there, are we? Right? Why not just do the integral? I don't. So the kind of roadblock to this, or the biggest challenge that this presents, is how do you find so many lowercase m's and m's? So we're not going to, like I said, we're not going to pursue this any further for just abstract functions. Let f be any function. But we are going to focus on a special case that Jackson mentioned, which is increasing or decreasing functions. So an important special case monotonic functions. What does monotonic mean?
One tone.
Yep. In calculus, it means it's either increasing or decreasing. Now, that may sound like everything, because those are all the possibilities, right? But it means, if we're talking about on an interval, if I say that f is monotonic on the interval from 0 to 5, I mean that f is either increasing all the way from 0 to 5, or it's decreasing all the way. It doesn't turn around and switch in the middle. Most of the time we'll talk about increasing functions. Decreasing is basically the same with a few minus signs here and there. So let's think about this sort of picture in the particular case where my function is just climbing the whole way. Suppose f is increasing on AB. All right, so redraw the picture so that now I'm just looking at functions that do something like this. And I'm going to chop this up into a bunch of subintervals. And I'm going to think about one particular subinterval, thinking about what happens between here and here. How do I find upper and lower bounds for the values of the function on this subinterval? Do I need to take a derivative and set to 0? The highest point's on the right, and the lowest point's on the left. Right? Simple as that. If it's increasing, on each subinterval, the right value, or sorry, the left value is a lower bound, less than or equal to f of x, which is less than or equal to the right value. F here is bigger than or equal to all these f values, which is bigger than or equal to f there. So what if I add up this fact over all my subintervals? So on my first subinterval, I know that this area is too small and this area is too big. And then on my next subinterval, I know that this area is too small and this area is too big, and so on. Well, these are just left and right endpoint Riemann sums that I'm building. So if I have an increasing function, the left endpoint Riemann sum is always smaller than the true value, and the right endpoint Riemann sum is always bigger. So the left Riemann sum is less than or equal to the integral. And that's less than or equal to the right Riemann sum. All right, so let's do an example. Let's see. Find expressions for the left and right Riemann sums for integral from 0 to 1 of 1 over 1 plus x to the 4th dx. 2, find an n such that the upper and lower bounds are within 0.01 of each other. So let's suppose I want to estimate this integral with a guaranteed accuracy of 0.01. I know that I can sort of trap it between the left and right Riemann sums. Actually, I still need to justify that by showing that that's monotonic. But let's use this error analysis to find a tight interval around that integral. This would be a pain to do by hand. Factoring x to the 4th plus 1 actually is a bit of a deal. Not straightforward. Okay, so the first thing to figure out is whether this function is increasing, decreasing, or neither. I'll come back at some point to the question of how you can tell that in general. What do you think? Increasing, decreasing? Well, the bigger a number is, the bigger its 4th power. So if x is bigger, then x to the 4th is bigger. And that makes 1 plus x to the 4th bigger. And that makes this reciprocal smaller. So the bigger I make x, the smaller I'm going to make this function. It's a decreasing function. So note f is decreasing have a little time to come back to and how you can check that things are increasing and decreasing. So in this case, things are switched around from what we saw a moment ago. The right Riemann sums are always too small, and the left Riemann sums are always too big. All right, so let's try to do this in terms of n. We'll leave n, capital N, undetermined. So in terms of capital N, if I choose my partition points, I have a width of b minus a over n, that's 1 over n. My partition points x0, x1, x2, dot, dot, dot. Xk is going to be the left-hand endpoint plus k times delta x, like a plus k delta x from Lansky. That's actually just k over n, pretty simple formula for it. The partition points this time. So on each interval, my left endpoint is xk minus 1, and my right endpoint is xk. Think about my intervals as going from xk minus 1, xk. So my left Riemann sum, I'm adding up my function at all of these left endpoints, and then times delta x. So let's pull the delta x out of the sum, as we often do. I have my sum here, and then I'm going to evaluate my function at the left endpoints. 1 over 1 plus k minus 1 over n to the 4th power. That's what a left Riemann sum is going to look like for this function. And a right Riemann sum is 1 over n times the sum of same thing, but now it's k over n instead of k minus 1. That's the only thing that changes. So I know that for any capital N, this is smaller than my integral, and this is bigger than my integral. All right. All right. So this, how you do this problem might depend on what tools you're allowed to use. On the homeworks, you can use more tools than on the quizzes. I want to show you a pretty nifty tool for Riemann sums that you can use if you're just trying to figure stuff out. And then we'll talk about how you can do it in a lower tech way, which is more like the quizzes. So, how many of you have used Desmos at least once or know what that is? Okay, good. So they have a Riemann sum calculator that's sort of set up to go, where you tell it your function, you tell it the number of partition points, and it sort of figures out the Riemann sum. Pull this down. All right, so here's the Desmos Riemann sum calculator, and of course it draws a picture, which is nice too. So we're looking at the function 1 over, parentheses, x to the 4th plus 1. And we're going from 0 to 1. So maybe zoom in a little bit here. And number of intervals. Okay, so let's choose the method. So c equals 0 is, I'm going to use a left endpoint Riemann sum. Then I'll flip it to c equals 1 and get a right endpoint Riemann sum. All right, so with n equals 12, I have about 0.887. I'm just going to write down a few values on the side here. N equals 12. My left is 0.887. And my right endpoint Riemann sum, I'm going to come down here and set c to 1, is 0.8455. So I know that the integral is somewhere between these values, which are like 0.04 apart. So that's a pretty good estimate. I've narrowed it down to a pretty decent range. But I want to get it down to 0.01. Well, I'm just going to jack n up and see what happens. Right, you can do a little trial and error here. Let's say n is like 50. Now my right endpoint is 0.8619. And my left endpoint, I'll set c to 0, is 0.8719. Wow, that's like right on the nose. How lucky is that? Okay, so these are 0.01 apart. And so at this point, I can say, thus, I know that my integral, which I'd really rather not do exactly, thank you very much. I know that my integral is somewhere between 0.8719 and 0.8619. And I had to use n equals 50 to figure that out. All right, and of course you can tell if I wanted more accuracy, I could just try bigger n, right? If I wanted 4 decimal places, I'd try n equals 1,000 and see if it worked. All right, no, keep going. All right, so that's cool. What if I don't have Desmos? Like, for example, what if I'm on a quiz or a lecture and I'm trying to get some points? So on the homework, feel free to do this. Like, it's actually good in my mind if you go use the Desmos Riemann sum calculator on your homework. I want you to see it. I want you to know the tool is there and practice using it. And but you also have to sort of know how to do things by hand once you've gotten a sense for what these Riemann sums are all about. Well, there's a particular trick that we can use here that cuts down the trial and error aspect of this. The left and right Riemann sums are almost the same. I'm adding up a bunch of function values, most of which are the same as each other. Let's suppose I do a left endpoint Riemann sum with n equals 100. I'm going to evaluate my function at x0, x1, x2, x3, x4, up to x99. Let's suppose I did a right endpoint Riemann sum. I'm going to evaluate my function at x1, x2, x3, x4, up to x100. Right? 99 out of 100 numbers on those lists are the same as each other. So, this is sort of a key fact. If I take the right minus left Riemann sums with the same n, okay, all those middle terms cancel out, right? So if I have x0 through x99 and x1 through x100, the only terms left that I'm subtracting are x100 and x0. In fact, it's just f of b minus f of a over n. Sorry, I should say times delta x. So f of b minus f of a delta x, which is the same as b minus a, f of b minus f of a over n. In the problem we just did, b minus a was 1, but in general. So let's suppose we want to get a little bit cleverer in this last problem, and I ask you, how big an n do you need to get 2 decimal places of accuracy? So going back to that last question, the difference between, I'll say, right sub n, this is where the notation isn't as bad, and left sub n is less than or equal to 0.01. So the method that I just used with Desmos was, well, just try a bunch of n's and see how soon they're within 0.01. But we can say I just need to solve this. F of b and f of a are 1 over 1 plus 1 to the fourth and 1 over 1 plus 0 to the fourth. So this is a half, and this is 1. Those are the values of my function of the right and left at the interval. So I just need to figure out how big this expression is. And b and a are 0 and 1. So the difference between right sub n and left sub n is, well, 1 minus 0, a half minus 1 over n. One times negative a half, this is just 1 over 2n. So if I want that to be at most 0.01, I'm just solving this inequality for n. Figure out how big n needs to be. All right, well, I can take a reciprocal of both sides. 2n has to be at least 100, and n has to be at least 50. Hey, look at that. That's the one that we sort of hit upon by luck before. And it actually was lucky. I didn't figure that out in advance. I just sort of guessed. 50 seems about right. Turns out 50 is exactly right. But now we can see for any error tolerance what it would take to get there. Suppose I wanted an accuracy of like 10 to the minus 6. If I take n to be like 10 to the 6 over 2, what's that, 500,000? I'll get that much accuracy. You can get as much accuracy as you want and you know how to get there. So, let's deserve the box. This is the key to error analysis with Riemann sums in the case where we have an increasing or decreasing function. This would apply whether f was increasing or decreasing. This is going to tell you the difference between the left and right Riemann sums, and you know that's the width of the interval, that the integral has to be somewhere inside of it. So this allows you to figure out how accurate these bounds are in terms of which Riemann sum we're looking at. So, all right, 5 minutes left. I want to say something about how can you tell if a function is increasing or decreasing. Well, the method you learn in Calc 1 is look at its derivative. So the Calc 1 method is if f prime is positive everywhere on the interval, then f is increasing on that interval. And if f prime is negative, then f is decreasing. F changes sign on the interval, it's positive somewhere and negative somewhere, then your function is not monotonic on that interval. But if it has the same sign throughout, then positive derivative means it's going up, negative derivative means it's going down. So with this function that we just had, like 1 over 1 plus x to the fourth, I could have taken its derivative using the quotient rule, or the chain rule, if I think about it as a power of -1. I could have taken its derivative, and it would have been like, I don't know, -4x cubed over 1 plus x to the 4th squared, and I could have figured out that that derivative is negative everywhere. I didn't do that, though, right? I just looked at it and said, well, the bigger the number is, the bigger the denominator, so the smaller the function. So there are some common hacks that I can use, and I'll tell you some of these hacks and then how to sort of justify them. So the sort of informal method is just look at your function and ask yourself, what if x gets bigger? Does my function get bigger? How do I know? Some of our basic functions, we should know some basic increasing functions, or basic, I'll say, monotonic functions. Because these are some of our basic building blocks for all of our functions. Like, e to the x is increasing. I know that because I just sort of know e to the x. I've got the graph in my head, it's going up. Same with log, that's increasing. Powers of x are increasing. So these are things that you should just know, right? Square root of x, the bigger a number is, the bigger its square root. Right? So we'll take this as a starting point. Like we have some just known increasing functions. If I take the sum or the composition of increasing functions, it's increasing. Yeah.
Is composition be multiplied?
No, although, let's see. You have to be careful with that because you have to worry about if it's negative or not. So composition, I mean something like this. Function of a function. Okay. So here's how I would look at something like square root of 1 plus x to the 4th. X to the 4th is increasing. That's my starting point, because I just know that about powers. Okay. Well, 1 plus x to the 4th is increasing plus increase, and constant functions we can count as increasing. Okay, we'll include that. So now I know that 1 plus x to the 4th is increasing. Now I'm taking the square root of something increasing. That's a composition of an increasing function with an increasing function. So the bigger x is, the bigger the inside is. The bigger the inside is, the bigger the square root is. Right? Square roots of bigger numbers are bigger. So now I know that that whole thing is increasing. Right? Suppose I took that and added on e to the x. Okay? Well, this whole mess is increasing because it's increasing plus increasing. Well, suppose I took the log of that. That's the log of something increasing. So the bigger a thing is, the bigger its log, that whole mess is increasing. I'd rather think that way than take a derivative, right? Because even after I took a derivative, I had to figure out how the heck do I know if it's positive or negative. So if you have these kind of increasing building blocks, and you know that they're preserved by sums and compositions, there are a lot of things that you can just look at and say, okay, that's an increasing function. And then finally, a common one that we've just seen is the reciprocal of an increasing function is decreasing. If you're talking about positive numbers. I guess that's another. So something like 1 over 1 plus x to the 4th. I'm looking at that and saying, okay, 1 plus x to the 4th is increasing. Okay, the bigger a number is, the smaller its reciprocal. So this is decreasing. Okay, so in problems that we do on quizzes or exams or whatever, I'll ask you to justify how do you know your function is increasing. This type of justification is totally fine as long as I can follow what you're doing. Like write out sentences, just say, the bigger a number is, the bigger its 4th power, and the bigger numbers, the bigger logs, and that's cool. That'll just be, maybe 1 point out of the 5 is that sort of explanation, but it is part of what we're doing. How do you know which functions are going up and going down? And then you can throw the Riemann sum analysis at it, compare the left and right Riemann sums and so on. All right, that's it for today. Have a good weekend.